For decades, animal welfare science operated on a strictly mechanical premise. The standard model evaluated an animal's well-being entirely through observable biological function and whether it could perform basic physical behaviors. Today, that standard centers strictly on sentience. We now recognize that welfare is defined by an animal's capacity to consciously perceive their environment and experience valenced mental states, what scientists call affective states. This shift requires us to discard old biological assumptions, particularly the concept of a bird brain. Avian neurobiology features a highly developed forebrain structure called the pallium, which functions as the equivalent to the mammalian cerebral cortex. This specific neural architecture supports complex cognitive processing. It enables long-term memory retention, complex forms of associative learning, highly sophisticated problem-solving skills, and the generation of distinct emotions. Because birds possess this conscious awareness, welfare assessments must account for their subjective experiences. But this creates a severe scientific bottleneck. We are trying to measure the internal feelings of an animal that cannot self-report. To solve that problem, researchers rely on a specific analytical framework. This flowchart illustrates the 5 domains model. Looking closely, the first 4 domains on the left capture strictly observable physical data. They catalog the animal's nutrition, physical environment, health, and behavioral interactions. The model dictates that these observable inputs funnel into domain 5. This final column represents the inferred affective state, the point where physical conditions translate into subjective, positive, or negative mental experiences. We can test the precise limits of this inferential framework by applying it to one of the most complex paradoxes in industrial agriculture: hypercapnic or carbon dioxide stunning. Evaluating an unseeable experience demands a strict hierarchy of evidence. Without it, we risk letting human intuition corrupt the scientific inference. Mass poultry processing operates on a staggering scale. Historically, preparing birds for slaughter required live shackling, a process that induces physical stress and high rates of injury. To mitigate this, the industry widely adopted controlled atmosphere stunning, using carbon dioxide gas. This method allows birds to remain in their transport crates, eliminating the handling and restraint of life shackling. Mapped onto our framework, this change improves domain 4 by restoring behavioral agency and removing fear-inducing human interaction. However, it replaces the atmospheric stability of domain 2 with a hypercapnic gas mixture. In mammals, breathing carbon dioxide is highly aversive. Humans exposed to just 7% CO2 report intense panic and a suffocating sensation known as air hunger. At concentrations above 40%, the gas causes severe mucosal pain. The immediate assumption is that a bird exposed to the same gas experiences the exact same suffering. But does that mammalian affective state translate across species lines? Anthropomorphizing the experience violates the assessment framework. To determine if birds actually experience this specific form of distress, we have to process the question through a rigorous hierarchy of evidence. The first filter in this hierarchy requires us to establish physiological and neurological homology. We have to see if the biological hardware even matches. The 2 respiratory systems operate on different physical principles. Mammalian lungs act like bellows, constantly expanding and contracting. Birds possess fixed lung volumes and a system of air sacs that creates a rigid, continuous, unidirectional airflow. Within this unique system, birds have specialized intrapulmonary chemoreceptors. These nodes make them highly sensitive to even trace fluctuations of inhaled carbon dioxide. The physical detection is demonstrably there, yet the specific neurological circuitry required to translate that sensory input into the subjective feeling of breathlessness remains unmapped in the avian brain. Because avian lungs and mammalian lungs process air differently, the sensation of air hunger that plagues mammals may lack the same adaptive evolutionary value for birds. Without that evolutionary requirement, the experience may not carry the same negative affective valence. Since anatomy alone cannot confirm the subjective experience, the hierarchy moves us to the next tier of evidence: observing protective behavioral responses. The raw observable data shows that chickens exposed to 30% CO2 exhibit heavy head shaking. They display an abnormal, open bill respiratory pattern and visibly labored breathing before finally losing consciousness. The critical experimental question here is how to interpret those actions. Are these automated physiological reflexes, or are they physical indicators of consciously experienced affective distress? To separate reflex from suffering, researchers rely on complex behavioral choice mechanisms, specifically approach avoidance testing. They construct environments where an animal must actively decide between enduring a noxious stimulus to acquire a high-value reward or escaping to a neutral zone and forfeiting it. The experimental findings yield a counterintuitive result. Broiler chickens will actively choose to remain in subnoxisective hypercapnic gas to continue feeding, even while visibly hyperventilating. This data isn't perfect. The gas itself acts as a rapid anesthetic which induces early immobility. This confounding variable makes it exceptionally difficult to measure true cognitive aversion. Still, the behavioral choices indicate that visible respiratory disruption does not automatically equal subjective suffering. Based on these experiments, scientists currently classify concentrations of 10 to 70% CO2 as only mildly to moderately aversive to the birds. Returning to the 5 domains flowchart, because birds lose consciousness before carbon dioxide activates nociceptors, we rule out mucosal pain. Applying behavioral data, we log the remaining negative experience in domain 5 as a mild to moderate aversion. To a human observer mapping their own respiratory panic onto the bird, this conclusion seems completely backward, but it is the direct result of rigorously derived scientific inference, detached from emotional assumption. Our understanding is not absolute. The hierarchy of evidence for carbon dioxide stunning remains incomplete, representing the very edge of current avian welfare science. Significant data gaps exist. We need conditioned place aversion tests after exposure to prove learned fear, alongside pharmacological studies using anti-anxiety drugs to verify the presence of actual panic. Until that data arrives, the 5 domains model acts as an essential scientific firewall, isolating factual observation from the bias of anthropomorphism. Demanding a rigorous hierarchy of evidence is the only reliable method we have. It is how we ensure that our industrial interventions genuinely improve the unseen, subjective, lived experiences of sentient animals.